So far in the course, we've been exploring different ways at looking at molecules. First, we started with the ball and stick model, the electron dot formula. Those you had seen before in general chemistry. The condensed formula. Then we moved to the bond line formula. That was something new for you. Now, recently, we've been seeing different ways when we introduced the chapter of stereochemistry. So first, we saw the Newman projections. Remember that these allow us to see from a bond, so we see the front and the back carbon in a bond, and those can be used in open chains like these ones here, or they can also be used for chairs. Then when we introduced stereochemistry, we started talking about dash and wedge, right? And that allows us to see how the molecule looks in space. And remember that again, we can see that in open chains or in chairs. And finally, we started looking at chair conformations. So this is another way of seeing a chair just like this one, but it allows us to see what the interactions between the groups that are in the chair are in the space. And now we're going to talk about a different type of projections, a different way of looking at the molecules. So the Fischer projections are used to represent molecules and molecules that have chirality centers. So the horizontal lines represent the attachments that are coming out, right? So these lines right here, these two, are coming out of the page, and the other two are going back into the page, right? So again, OH here and H are hugging you, they are coming towards you, and then the ethyl and the methyl are pointing away from you. So the Fischer projections are very useful because we can draw a bunch of multiple different chirality centers all at once. So you see in here, each one of these cross lines is a chirality center. So you see in here we have 2, in here we can have 3, and it's very easy to identify them when we draw them like that. Here we have 4, right? So just so you can picture it, this is a Fischer projection. This is how it looks like. This is how you should picture it in your head. So the H and the Br are coming towards you, and then the CH3 and all the carbons are in one plane. So here we're seeing it from the side. So this CH3 right here would be the CH3 here, and you see all of these are in the same plane, right? They are pointing towards you, and then you have the H and the Br, the Cl and the Br, and the H and the O that are all coming towards you. They are kind of embracing you. So the Fischer projections are very helpful when assessing the relationship between a pair of molecules. As you can see here on the left side, we have 2 enantiomers, and it's very clear to see because they are completely mirror images, so those will be enantiomers. And on the right side, if you try to draw a plane of symmetry, you'll see that these 2 molecules are not fully reflections. So this center hasn't changed, but this center right here, it's flipped, right? So because not all the centers in the molecule, not all the chiral centers in the molecule are flipped, this molecule is a diastereomer. So remember, an enantiomer, all the centers are flipped, and in a diastereomer, not all the centers are flipped. So how can we assign RNS when we're looking at a molecule through a Fischer projection? So it's very simple. We use the same process that we used for any other molecule. But remember that when we had a molecule that looked like this, we always had to have the 4 in the back to be able to assess if it was R or if it was S. So very similarly, here what we need to have is the 4 pointing up. And so when the 4 is up like that, then we can use the exact same rules that we were using for RNS in a molecule that looked like this one, like with wedges and dashes. So if you put the 4 in the back, like we have here, if 1, 2, 3 goes clockwise, then it would be R. And if 1, 2, 3 goes counterclockwise, then it would be S. I'm going to say it one more time. So in order for a Fischer projection to tell us if the molecule is R or S, or if that particular center that we're looking at is R or S, what we need to do is have the 4 at the top position. You see, a Fischer projection always has 4 positions, so the 4 has to always be there. It doesn't matter what you have in 1, 2, 3. And then if your 1, 2, 3 follow a clockwise setting, then it will be R. But if it follows the counterclockwise, then it will be S. So how can we accomplish having that 4 position at the top? There are some movements that we can do among the 4 different groups and some that are not allowed. So remember that when we have something that looks like this, and we have the 4, imagine we have the 4 there, and the 3, 2, 1. One of the ways that we can accomplish having the 4 in the back will be to do 2 swaps, right? So we could swap 2 and then swap the other 2, and that will give us the same molecule back. So that will tell us the stereochemistry of that center. So when we are looking at Fischer projections, that still stands. So you can move you can do 2 swaps of 2 pairs of groups, but there are other movements that you can do. So look here, if we swap this group from the top to the bottom, that is allowed. But what it's not allowed is to swap the 4 of them, just like this one. If you put Y over W, and then that is not allowed. So that is not allowed. And then what you can do is, if you keep that one right there, you could rotate 3 of them. And here they are rotating it clockwise. Here I'm rotating counterclockwise. It doesn't matter. So again, you can swap 2 of the groups, or you can do 180 degrees, and all of that will give you the same molecule back. So remember that a Fischer projection that looks like this is the same. You can put it in the plane like here, and then you can start doing those rotations. So again, you can swap 2 of the groups, you can interchange something that is in the top and at the bottom, but one thing that you cannot do, remember, is to, and I'm going to go back, you cannot rotate them 90 degrees just like that. So that is not allowed. Okay, so you can swap 2 groups, you can change top and bottom, but you cannot rotate them 90 degrees. So imagine we have a molecule that looks just like this one. It's a little more complicated than the ones that we've seen so far. So let me just redraw it here. So I have the OH, the H, the CH3. Then here I have the H, the amine, and the carboxylic acid on the top. Okay, so let's first assign the priorities and understand why these priorities are what they are. So hydrogen is always going to have the 4. Then here on top I have a carbonyl, here I have a carbon, and here I have a nitrogen. So because nitrogen is heavier than carbon, this is going to get my priority number 1. And then I have to compare between the 2 carbons. The carbon on the top is connected to O, O, O. Why is that? Because it's connected to the carbonyl twice, so that counts as 2 of the O's, and then it's connected to that O. So that's 3 oxygens. And here at the bottom, this carbon is connected to OCH. Because of that, the one in the top will get my 2 priority, and the one at the bottom will get my 3 priority. So one of the things that I really like to do, especially when the molecules start becoming more and more complicated, it's to simply take the center that I'm looking at, this one right here that I'm pointing out, and I will simplify it. So I know that at the top I have my priority number 2, that at the bottom I have my priority number 3, then I have 4 on the right, and I have 1 on the left. And so this is a technique that you can also use for your RNS. When your molecules start getting bigger and bigger and it gets complicated, what you do is that you simply take the molecule and simplify it. You just need the groups. You just need the priorities. And so what am I going to do now? All right, the 4, I know that it has to be in the top. Don't be tempted to say, okay, I'll put 4 on 2, 2 on 1, 1 on 3, and 3 on 4, because that is not allowed. That's the only movement that is not allowed. One of the movements that it's allowed, though, is if I put the 4, I can move the 4 180 degrees, but that doesn't help me, because if I put the 4 where the 1 is and the 1 where the 4 is, that doesn't help me. So what am I allowed to do? What you can do is to make 2 swaps. You can say, okay, I'm going to put the 2 where the 4 is and the 1 where the 3 is. If I do that, and you see how simple this is, I don't have to redraw the whole molecule every time. So now I'm going to have the 4 at the top as I want to, the 2, then I'll have the 1 at the bottom, and then I'll have the 3. So now, because I have the 4 on the top, that's great, that's what I want. And so now I look at 1, 2, 3. Because the rotation is 1, 2, 3, that's counterclockwise, this molecule is S. So I can say that this center right there is S. And you see, you don't have to draw the whole molecule every single time. And this is something, let me remind you, that you can also use in when applying RNS when you have a molecule like this. Okay, and finally, so remember, this is one of the techniques that we use. We swap 2 of the groups. But the other thing that you could do if you wanted to, and here you have a few examples so you can look at them, is to say, okay, I assign the priorities, 1 for the nitrogen, 2 for the carboxylic acid, 3 for this group at the bottom, and then 4 for my hydrogen. And then I look at 1, 2, 3. Because that rotation is clockwise, but the 4 is not where it should be, it looks like an R, but it's actually an S because the 4 is not where it should be. Okay, so you could either do what I did before, where I swapped 2 of the groups, I got the 4 at the top, and then I assign clockwise or counterclockwise, or you can say, okay, my 4 is not where it should be. That's fine. So now I look at 1, 2, 3, and I say, because the 4 is not where it should be, it's going to be the opposite. Here you have a few examples of that, so please stop the video here and make sure that you understand this way of assigning RNS in Fischer projections.